let's finish a couple things in 1.4. First property has to do with span of the constants, like the solution. Let A be an n by n matrix. Then the linear system so the linear system of A and B, I probably should have written that down. So if you have the linear system AX equals B, that's consistent, meaning it has a solution or an infinite number of solutions, if and only if B is in the span of the column vectors of A. So that's another way of saying basically the column that B is in the span of the vectors. It's what we did up here. But we also did in an example in problem session, which I'll probably pull that up as well and talk about it. Another definition I did not cover was pivots. So for a matrix, the first non-zero entry in a row is the pivot of a row. So let's go back up and just look at some matrices. So this one, so this would be the pivot of the row of row 1. This one here is pivot of row 2, and then there's no pivots in those two rows. And that's meaningful if there's no pivots. That means you have a underdetermined system and things like that. Let's go back here. So pivot, pivot, no pivot. And then back here, there's a pivot in each row, and it's on the diagonal. So this being the identity matrix, very meaningful. Going back here, let's see. So this is not row reduced. So once you row reduce, then you end up getting the pivots or not. Not too critical of a definition, but it'll come up in terminology. Okay. So there's a discussion of elementary matrices in 1.4. We will do that in 1.5. And it basically is used to help mostly for proving theorems and things. Not really too many for operations. Then numbers 25 through 28. Determine whether the vector is in the span of of these vectors. So is B in the span of those different vectors? And so we did problem number 25 in problem sessions, at least row reduction. So what you do is you basically convert all of the vectors to column vectors, form the system like that, and then you do your typical row reduction. So this question, let's see if I could find it handy. I think I might have erased it. Let's just check and see, since this is a short video. Let's see. I think it was down here. Well, we're going to be going through all of this, so don't write it down. Don't pause it yet and write it down. Let's see. Yeah, here it is. This one. So we did this in... just copy that. I'll bring it back over. And let's go ahead and erase all this stuff. So this is how you do it. You want to practice a couple of these, and it has some other implications later. This is one of the homework questions. Number 25 on page 69. So here's B, V1, V2, V3. So this is how you're setting it up. So is B in the span of those vectors? Meaning every linear combination, is there constants R1, R2, R3 that would make up, like construct or make up B is the question. And I'm going to fix that because I've seen that there just to be consistent. Okay. So I set this up kind of how you would really think about it. So you have R, S, and T just to be simpler. And then here's your column vectors. If you multiply out and add, you basically add straight across, and you get this form. And it's equal to your vector 3, 5, 3, so it's here. And then you set this up into your augmented matrix and then do your row reduction. So this is the row reduced echelon form to here, and then you can see you have a solution. There is and exists a solution right here. So if R is 2, S is 0, and T is -1, that is basically makes up B. So that would be the span of one of those vectors. When you do that, you get B, which implies it's a solution. So even if you had an entire row zero out, we would also have that it's in the span. It would be a bunch of those vectors essentially make up B, in which case it would be like two planes maybe intersecting in a line, and then there are a lot of possibilities to make up the vector B if it's an infinite number of solutions. So that's the idea. All right, so consider that some of the notation of how this is constructed, and we'll developing kind of equivalent conditions, equivalencies for all of these different ideas. Okay, well, we'll just make that a short video and move on to 1.5 next. Just wanted to cover that. There are a few more topics that were in 1.4, but I'm not going over them directly in particular because they're a little more involved than we need, but take a look at some of those theorems. Okay, now let's go on to 1.5.